of the IAF Workforce Development YPP Committee, as well as the Space Systems Committee, and I'm excited to be moderating for all of you today an amazing panel of our wonderful IAF committee members from the Space Systems Committee talking through space systems engineering and kind of what's the latest and greatest, as well as how our next generation is playing a very pivotal and critical part and how we see that changing in the future. So I'm going to start off by introducing our amazing panelists we have here today, starting off with Matteo Emanueli. Matteo is a manager in the strategic development and new markets team at Airbus Space Digital. He's also the current co-chair of the Space Systems Committee. Next, we have Dr. Mamata Maheshwarappa, who is the head of research and development within the office of the chief engineer at the UK Space Agency. After that, we have Ms. Jill Prince, who is the director of the research directorate at NASA Langley Research Center. And Jill was also the previous chair of our committee, and is now supporting us and has amazing experience to bring to the table. Next, we have Ryan Demney, who is the configuration lead for the Mark II crew lander at Blue Origin and is leading the mechanical design and integration of Blue Origin's flagship lunar human landing system set for flight in 2028 for NASA's HLS contract. After that, we have Hamed Gamal, who is a systems engineer for Mynaric and UN Peacekeeping. And last but not least, we have Daniel Wishart, who is a systems engineer and team lead in the European Space Agency's concurrent design facility, where he leads a multidisciplinary study to explore feasibility of future space missions and new spacecraft concepts. And I forgot to introduce myself. So I work at Lockheed Martin Commercial Civil Space in Denver, Colorado, and I'm currently supporting the GeoXO program, which is the next generation weather satellites, bringing weather and climate data to the United States. And with that, we'll kick it off. But before we get started, I want to kind of hand the mic over to Matteo to kind of talk about the Space Systems Committee, as well as how to join if anyone is interested. So, Matteo, feel free to take it away.
Hello, Sapna, and as well, hello everyone who is listening. So I think the committee most visible activity is certainly managing the Space Systems Symposium, or as we call it, the D1, and this is done at each international congress. So the committee manages and leads the 7 technical sessions of the symposium, covering innovative concept, enabling technologies, emergent and cooperative space system, then all the system engineering, modeling, analysis, methodologies, and processes, and last but not least as well, lesson learned. In practice, what we do is to review and evaluate literally hundreds of abstracts every year. And to give the audience a dimension, this year we are at 345 abstracts so far, that are divided in 8 sessions of the symposium, 7 technical and 1 interactive. This is a very important and also difficult task, because the field of space system is broad and is also rapidly evolving. Especially in the last year, we have seen the surge of AI application for space system, for example. It requires our members to remain up to date with new technologies and development, and that we maintain inside the committee a vast knowledge bases. The committee serves as well as a networking platform for industry veterans and young professionals from different backgrounds. And we actually select the brightest and the most passionate young professionals, as you will see from these panels, to join the committee. And this create a bridge to exchange ideas on technology, methodologies, and so on. One of the questions that as chairs we receive more often is how to join the committee. So usually new members will need a recommendation from either an existing committee member or an external recommendation, like, for example, from the IAF Secretariat. We then circulate the candidate's resume among the committee members, and we invite those candidates to present themselves in person before the committee at one of our regularly scheduled meetings, so either in Paris during the spring meetings or at the IEC during the September-October timeframe. And then we vote to accept or reject the candidate. I think what is very important for new members is that they are not only bright and passionate, but also will remain actively involved and will commit in attending in person both the ISE, of course, but as well the spring meeting in order to help us managing the symposium and all the many hundreds of abstracts that we receive every year. Back to you, Sapna.
Great, yeah, thanks. I think this is really nicely outlined, so I hope a lot of people who are hoping to join now have a clear path, and of course we can answer any questions at the end if there are more. So next, let's get into the main conversation topic, which is space systems. So first off, we'll start with Marcos and Ryan. Could you describe the role of the next generation in space systems and kind of what that means to you? So we could start with Marcos.
Yes, of course. Thank you, Sapna, for this question. I really appreciate it, especially because it's one that I ask myself often. And what I mean is I often ask myself what kind of impact will I like to have in my company, in the project that I'm involved at, but also the impact that I would like to have alongside my career as a young professional and as a space systems engineer. For sure, one of the things that I have noticed is that, as we come fresh from college, we are more new and more aware of new ways of doing things, new ways of tackling the systems engineering process. One of those for me has been implementing model-based systems engineering tools and methods. So that has been, I guess, part of a large part of what I have been doing throughout my career at Airbus, at the French Space Agency, and now at my current company, the City Engineering Group. And that has been a lot of change management per se, sitting down with domain experts, sitting down with people doing systems engineering for 20 years already and telling them, okay, this is how the process is done. This is how it looks like in this new format, in this new framework, in this new set of tools. It is the same process, but it is now more streamlined because it is more interconnected, because now people, we have connected models, etc., etc. So all of these things have been, I guess, one of the things that I have been able to bring to the table, that I have been able to contribute to in the project that I've been involved in. And I think it's greatly appreciated because, again, these new ways of doing things also help us build better systems with higher quality that are also less expensive to build and hopefully faster to develop. I do think personally that another contribution that we can bring, and that it is really our responsibility, is that of being better learners, let's say. I guess we all can relate to having an issue of systems engineering. Again, it's a process, right? So things have been done before, but somehow in a new project, sometimes it seems like information is scattered and those lessons learned from previous projects are not really well documented, which means that in many ways we have to start from scratch, and that is very frustrating because we know we've done this before, we know we've done it well, and unfortunately we are not always able to leverage that experience. So I think as a young generation we also need to be better learners in that way, to be able to make sure that we capture the essence of the work that we're doing right now, so that at the end of the day, we help out developing the project that we're working on, but we also help out the next generation in doing the same in their project.
Very cool.
Yeah.
Great to hear about your experiences. Daniel, you could go next.
Daniel or Ryan?
Sorry, Ryan. My bad.
Yeah, so from my perspective at Blue Origin specifically, I think the next generation could help us on focusing on efficiency and building at rate. So a lot of companies and space agencies now, they have a lot more ambitious goals of building launch vehicles and lunar human landers and communication satellites at super high rates that were never really dreamed of before. And that's what the new fresh generation is going to really be helping us with. People with younger experience are better at using new digital tools, as Marcos mentioned. And they have that systems thinking kind of oriented mind that's great for MBSE and digital tools that some heritage systems don't really use right now. But they need to be able to apply that to helping these companies build as fast and efficiently and as safely as possible to get to rates that previous space systems just aren't at. Young people are great at focusing down on optimizing really small issues for single iteration vehicle builds, but we need to know how to apply that to really high rate vehicle builds. We need to know what's the quickest system to build, test, and fly safely. Helping us do that and being able to make sure it's manufacturable is really going to help systems engineers advance in today's world.
Great. Yeah, thank you both for your insights. Next, we're going to pivot a little bit and kind of go back to the fundamentals. So, Mamatha, could you please describe for all of us the job of a systems engineer and what that kind of looks like for you in your experience?
Yeah, definitely. Thank you. The analogy I would use is that a systems engineer is like the conductor of an orchestra. Like how each musician is highly skilled at their own instrument, each technical team is an expert in their own domain. The conductor need not play every instrument. Instead, they make sure everything fits together, stays in tune, and delivers the final performance smoothly. So similarly, a systems engineer makes sure that all parts of a complex project work together. It could be technically, logically, and safely. To deliver an end-to-end system that meets the mission's goal. So in order to achieve this, the systems engineer needs to firstly understand the whole program, not just parts of it. And they look across the entire system. It could be the spacecraft, the payload, the software, operations, and even safety. And they make sure it all works together as one coherent system. And then they turn those like high-level mission statements or objectives into clear technical requirements. That comes from users, stakeholders, and what they want to achieve, and then translate that into specific and testable, most importantly, testable requirements that engineers can design, build, and verify. Following that, they help also to define the system's architecture, showing how subsystems connect, communicate, and operate as a single mission. More often than not, they also balance trade-offs and manage risks. Trade-offs could be like performance versus cost, schedule versus risk, innovation versus reliability, and also systems engineers help teams make informed decisions with the consequences clearly understood. They coordinate across multiple technical teams as well. They keep in mind mechanical, software, mission, payload, and operations, making sure the teams are aligned, they're all moving in the same direction towards the same goal. They also make sure the system has been designed actually works. And they do that through verification and validation process. They ensure every requirement has been met and that the system behaves exactly as intended. And finally, they document key engineering decisions. They capture how the system is defined, why decisions were made, and how the mission will be delivered, creating a clear technical record of that whole program and that others can rely on. So this role is critical in all sectors, but particularly in space because they are very expensive and high risk. So systems engineer helps reduce that risk, avoid expensive last stage redesigns, align technical decisions with mission objectives and policy goals, and finally deliver missions that actually achieve their intended outcomes.
Amazing. Couldn't have said it better myself. What a great description. Thank you so much. So next we're going to take a stroll down memory lane and going to Jill and Daniel, what made you first decide to enter space systems and kind of what was your journey into that field? We can start off with Jill.
Okay, thanks, Sapna. And it's very interesting that Mamatha made the connection between the conductor with the person who doesn't play the instrument, which is when I came up through the field, that was not the culture that was prevalent 20, 30-ish years ago. And back then, when I was going to school, there really weren't any formal degrees in systems engineering, at least that I saw, that came with experience. And what I was told when I graduated was that you had to be really good at one thing before trading that depth for breadth. Now I think it's a little bit different, and you can learn that systems engineering perspective earlier, and I think that's a really positive thing. It just changes your way of thinking and in being more inclusive. And the earlier you gain those different perspectives, I think learning the connectivity and the influences that one discipline has over another is really important to have early on. So for me personally, I graduated with degrees in physics and mechanical engineering, and my experience was in flight dynamics and trajectory optimization. And with increased roles and responsibilities, I got more systems approaches in my work. My technical career was in Mars entry, descent, and landing. I worked on Mars Odyssey, Mars Reconnaissance Orbiter, and Mars Phoenix Lander. And each one of those, I had to consider the effect of the one discipline on the other. For example, like the thermal impacts of drag on the solar panel and how deeply the orbiter should go within the atmosphere and its future trajectory. So there was aerodynamics, there was thermal implications, there was flight trajectories, and that really gradually morphed into systems thinking. Um, my career was augmented with formalized training. NASA is really good about offering coursework and studies, taking a couple weeks out of my work efforts to learn and develop. So I took a lot of those programs. I was involved with a lot of those programs, and eventually, just my career just evolved into its own trajectory. And I started leading groups of systems engineers and workforce development, organizational change, and that very much encompasses a systems engineering approach. So that's how I've evolved over the course of my time within NASA.
Great. I like how you kind of mentioned the breadth versus depth piece, because I think that's something I bet we've all dealt with in our careers, toying with that, or maybe we started from a deep specific topic and we went up into systems. But I think it's good, yeah, to hear your perspective, how you've seen that change now.
It's different ways of thinking. I mean, it's the culture is evolving with the new skills that are learned earlier now.
Yeah, definitely. Daniel, would love to hear your thoughts as well.
Yeah, how did I get into systems engineering? Maybe I want to think that growing up playing Lego brought me into engineering, and I like to build things, be creative in the broad sense, and I was always fascinated about airplanes, to be honest. So I studied aerospace engineering, and only in those studies I realized the different subsystems that exist in complex systems, and then I pivoted into space engineering, but still system engineering was not something that was really offered as a course at university. It's not something I really grasped as a discipline in itself. It was more the subsystems. And as Jill said, you become good at one thing. You become a mechanical engineer, you become a thermal engineer, propulsion engineer, and all these, actually very interesting domains of space engineering. My problem was I couldn't decide what I wanted to focus on at university. So I dipped my fingers in all subsystems a bit, became a specialist, not in the sense of being specialized in one domain, but being specialized in the holistic view, getting to have an understanding of all subsystems. And what really made the leap then into systems engineering was an opportunity I got at ESA when I joined the graduate trainee program in the system engineering domain, and really managed to actually build upon what I had learned and structure that and learn about different things like the ECSS processes and all that thing. So all my background from university was then brought into play, and I shaped it into systems engineering. And ever since that time, I've expanded upon building my system engineering competence. For example, like joining also the IAF technical committee to exchange with people who do system engineering differently and just learn from others. And so it all kind of evolved in a way that I hadn't foreseen, and here I am, and it's a very interesting domain to be in.
Yeah, it's great to hear how kind of like one program really changed your perspective and your career trajectory. And I can definitely relate to not being able to choose a specific major. It's hard. But I have a follow-up question. What's your favorite Lego you've ever
Yeah.
built up to now?
Oh, I'm gonna pick a more recent one, and I'm just gonna say
Yeah,
the Saturn V model that came out maybe a few
yeah,
years ago. That one, we've probably
that
all
one
got
was
it on
too
our
cool.
shelves, to be honest, and I enjoyed building
Yeah,
that one.
I think it's a requirement for anyone
Yeah,
in aerospace to
exactly.
have that one. Great. Thank you both for kind of defining or kind of explaining how you entered space systems and yeah, it's kind of different for both of you, so it's really interesting to hear. But next I want to, we've been talking about entering the field. Now I want to talk about why is it important? So, for Hamad, could you kind of go through why you think space systems engineering is essential for a space mission or a space program?
Right. Yeah, in all honesty, if you ever go to any mission that have ever had failure in orbit and you look closer, you will see that components and little subsystems or major even subsystems on a spacecraft or on a launch vehicle don't really cause the mission failure. It's usually interfaces, it's usually mismatches of requirements and whatnot. So if you see the grand scheme of things, missions don't really fail due to component level failures. They fail due to system level failures. And then comes systems engineering, which is basically the grid that connects all of them. If you have a perfect propulsion system, if you have perfect avionics, if you even have some sort of harnesses and look at even the connectors as a subsystem individually, if you don't get the timing correctly, the requirements, the interfaces timed up in a coherent manner from an engineering point of view, from systems engineering point of view, you always will guarantee yourself either having to rework or having to revise your designs or having to go back and reiterate again, which is the foundation of why systems engineering is fundamental for spacecraft missions and for space missions in general to guarantee their success. And if you look at the current ecosystem and the current atmosphere in the ecosystem, I will fall back to something that Marcus and Ryan mentioned earlier, which is if you look at the young generation upcoming and how articulate and how really keen they are on optimization, you always need to balance this when you look at the failure rates that we have been collecting, not even by opinions, but by factual data from the FAA or from the GAO office. It have been 10 to 12% of the failure rates still existing in the space missions and the space launches, and this rate is in the era of new space, which is from the early 2000s. And when you look to the historical rate, it have also been 10%. So nothing really changed when it comes to percentage of failure, while all our methods and methodologies have been modernized. And when you take a closer look on why these failures exist, it's almost guaranteed that it is a system level failure, and it's either of delaying systems engineering or ignoring it at the first place and then having to go back and reinstating it in different forms or as in different nomenclatures. So I think the foundation of space mission success relies in correctly integrating systems engineering early on. It's also factual figures that NASA published a couple of years ago of that 70 and 80% of the life cycle pricing is set at the beginning of the mission. So when you ignore such pillar like systems engineering and say, okay, you will iterate and failure is a mean of success and whatnot, you eventually pay this back as a technical debt, and you eventually do this again. However, it comes at a higher expense. So systems engineering really matches the economy of how you run a space mission. So it's not just connected to the success; it's also connected to the expense of when you provide a space mission, how much it will cost you to generate a successful mission.
Amazing. I think you've sufficiently freaked us all a little bit out knowing how important space systems is. And I think now we're all wondering, how can all of us demonstrate the systems thinking mindset, even if we're not systems engineers? So let's say you're a mechanical engineer or even doing things like policy or business development. How can we all take that mindset into our daily jobs? So Marcos, I'll let you kind of answer that, for the audience.
Yes, thank you, Sapna. I actually feel like the stakes are quite high because that term has come out so much already in the beginning of the discussion, systems thinking, and it's definitely something important to explain. Now, this is my personal perspective of what systems thinking is, if I were to put it in a single sentence, and that is simply understanding how your work affects the rest of the system. And the way I like to see it is that, you have both upstream and downstream impacts. What I mean by downstream is a bit what Jill was mentioning when we talk about engineering that, let's say you have system level, you have subsystem level, component level, and there's engineering that is done at every level, right? So regardless of where you are, if you are a systems engineer or a mechanical engineer or an electrical engineer, or perhaps you're just building this very small part of the system, it all fits together at the end. And the engineering decisions that are made have an impact if you change a requirement, and or like Ahmed said, if at some point you're going to be making change at an interface, it is important that this information is properly communicated, properly explained to the people or the teams involved. And I would say that having an understanding again of the impact of your work on the downstream is very important, because as Hamed properly said, interfaces, these exchanges, these interactions between the different elements of a system is often where space missions fail. What I mean by upstream is actually more on, a project, a space mission has different stages, and that is also something that we need to consider. When we are defining a mission architecture, we're also defining all the systems that will be built later on. And when we design the system, when we build the specifications, we're also imposing constraints and limitations on how these vehicles are going to be tested, how they're going to be verified and validated, how are they going to be operated. All of those things have an impact on the life cycle of the system, and these decisions that we're making will also have an impact on how long is the system going to take to develop, how much is it going to cost. And again, like Hamed already said, doing systems engineering early is quite important, because otherwise the cost, especially, and the development time can skyrocket, and it can also become a very lengthy development process. I would say, in addition to that, and to finish off, being a good communicator, being able to speak different languages. You talked also business. We often also have to translate information to management, so that decisions can be made, so that parts can be bought, so that contracts can be signed. And that also, I think, leads to the conclusion that people are also part of this system, right? And being a good systems engineer and having this systems thinking also means that, we have to be aware of how we are interacting with each other, and the impact that we're having on the team in general, right? So again, communicating information effectively and being able to lead the development effort forward.
Awesome, Marcos. I wanted to actually highlight what you said with an example, because I feel like I work with examples. But let's say, for example, we have the command and data handling system has the computer, like the brain of the spacecraft, and then we have the power system, and then we have, in this specific example, propulsion, which maybe has valves to actuate thrusters so that we can move around. So let's say I'm a propulsion engineer and I have a valve I'm trying to choose between. Now it's like thinking about it, what are the impacts? What other subsystems care about that? It's, the C&DH subsystem cares about it because then they have to send the command to actuate it. The power system cares because they have certain power requirements. Harnessing matters with how it's connected. The guidance navigation control team, because they have complicated algorithms that rely on these thrusters. Almost every single component on the vehicle is connected to other components or other teams. And so I think, Marcos, you definitely hit the nail on the head there. It's extremely connected, and you can only kind of work through that by communication. So thank you for kind of explaining that. So next, we're going to look at kind of a hot topic, which is artificial intelligence, but also not just AI, but new technologies as well. So like anything that's new and upcoming. So I wanted to get an idea this time, asking Daniel and Ryan, how do you all see these new technologies and AI impacting our common systems engineering processes, like making systems models, requirements verification, etc. But yeah, what do you see that looking like? And we could start with Daniel on that one.
Yeah, it's certainly a hot topic. We're all here in the age of AI. It's been we've been confronted with it, and it's certainly also here to stay. It will fundamentally reshape system engineering, I think, across models, requirements, verification, not just how we manage these, but also how we as system engineers will collaborate with other engineers and make decisions. I think that's clear. For system modeling, I think we're moving now towards something that's like a fully integrated environment. We had last year released the ESA Technology Vision 2040, kind of a document that outlines all critical technologies that are providing strategic autonomy in the next 15 years from last year's point of view. And concepts that are linked to AI, digital thread, high fidelity digital twins have become central in this document. So these AI models that evolve over time, support faster trade-offs, generative design maybe even, have become key also to the system engineering domain. So things that are really dynamic rather than a static software or something that we might use. And then you mentioned requirements engineering. I think we're all very aware how complex these space systems are, and might even become more complex going forward. So I think when we think of autonomous spacecraft, like onboard autonomy, distributed constellations, things like this, they are really making a space system more complex than what we've seen so far. So with all these interconnected requirements, I think AI can really also help support consistency, traceability, detection of conflicts, help us reduce risk overall, and hopefully optimize development time down the line. Let's see. So I think, these future technologies, they're here to stay. Here at ESA, we have the Future Engineering Division. We're injecting these new technologies and maturing them, exploring AI-assisted engineering, model-based approaches, digital continuity across life cycle and different mission phases. We have the concurrent design facility, where we can also explore these new concepts and really test them in a rapid way to see if they carry the fruits that we claim they do. So I think from my experience, these future technologies will hopefully help us do our work, not necessarily do our work for us, but make it more manageable in a sense for a system engineer.
Great, thanks. And Ryan, love to hear your thoughts as well.
Yeah, so on AI specifically, at Blue Origin, we're using AI to make the processing and connections of models in these systems areas quicker and more efficiently to iterate through design and analysis cycles. So I don't think I have to tell this panel, it's not uncommon to have your requirements and analysis models and interfaces all in different pieces of software, right? You're doing requirements in your management software. The interfaces are all in Cameo with the functions, and then you have like an ANSYS analysis suite, and then the hardware design is in a CAD software, and you have translation softwares between all those things to talk. But we want to iterate through all those things faster before we go run an ANSYS model that takes 12 hours just to see how a design change is going to help us verify a requirement. So, we can show all these things to our AI models, get them to interpolate the data and say, how can you best help me achieve this type of performance? What design change can be made? What requirements change can be made? And kind of act on that before we go set up for the ANSYS 12-hour run. So that's helping us make decisions quicker. To me, that's one of the best uses of AI in our industry. So we're trying to have it help us identify the system trends we need to make better optimizations.
Amazing. And I guess a follow-up question for both of you. How how do you see systems engineers interacting with AI? Like, are we primarily verifying the results? Are we providing training data? Like, how do you see the role of a systems engineer kind of adapting and changing as AI becomes more in the loop? And we could
Yeah,
maybe start with Ryan. Yeah, go for it.
Yeah, I mean, systems engineers definitely have to be using AI as a tool at their disposal. And to go with your question, are you supposed to use it on the front end or the back end? It's going to depend where you are in the analysis cycle. It's definitely going to help you write better first iterations of requirements when you're at the preliminary design review. And then when you're at the tail end and the critical design review, it's going to help identifying your driving requirements in the design that have helped you get to where you are today, and potentially help you identify bottlenecks at the CDR to help you get out of jams when you need to squeeze more performance out of the system.
Yeah, definitely agree. Daniel, curious to hear your thoughts as well.
Can you repeat the question just quickly?
Yeah, how do you see systems engineers kind of interacting with AI? Is it more like, providing inputs into the AI models or verifying results, or
Yeah.
how do you see that shaping?
I think I think it's twofold. I think on one end you use AI just as a means to do your work. It's purely an assistant to optimize workflow that might have required manual work. For example, I would say requirement checks or traceability, just things that require logic, and you could train an AI to do these checks for you. On the other hand, I think you can also be, really a user of AI when it comes to things like digital models, where you have early on you set up all your digital twin, and then down the road you want to use this, or maybe you want to use AI to have like a generative design based on that and see how that evolves. It's a bit what Ryan mentioned with the early phase reviews and the later phases, and AI carries different focuses in different parts. I don't want to repeat what he said, but I'm fully in agreement.
Yeah, I'm excited for not doing all the labor-intensive, redundant, boring work and doing
Yeah,
more
exactly.
exciting, brain-heavy work. But hey, we all had to do it to get to where we are now, so definitely important. But after you're more of an expert, we can automate some of that. But yeah, thank you both for touching on that topic. I had a personal just curiosity too. So next we're going to continue looking down the road at the future. So 10 years down the road, I want to hear from Amata and Hamed. What do you guys see systems engineering looking like and changing?
Yeah, thank you, Sapna. I feel space systems engineering will still be rooted in rigorous thinking 10 years down the line, but probably the center of gravity might have shifted. What I mean by that is a couple of things that we are already seeing some changes is the digital threads become critical to the infrastructure, such as like models-based systems engineering matures. It is no longer static documentation. It becomes a living executable system model that is connected to simulation, test, operation, and program controls. And that becomes the source of truth across the full mission lifecycle. And the way we conduct reviews will surely change, and they'll no longer be slide-based events. They become real-time snapshots of system state pulled directly from the thread. Assurance evidence flows continuously from simulation to hardware in the loop, assembly integration and verification, and also on-orbit telemetry. Secondly, Ryan and Danielle already mentioned AI augmented engineering and operations. So AI co-pilots support engineers not by replacing them, just by increasing the leverage. And they assist with what we already discussed, like requirements quality, interface consistency, even probably fault detection, isolation and recovery strategy synthesis, and verification, validation, coverage, etc. Mission operations evolve from scripted playbooks to closed loop autonomy with humans firmly in the loop, for sure. Safety cases might evolve too. Where we will surely retain humans is framing the mission's value, setting risk appetite, embedding ethics by design, and probably critically negotiating where policy, security, sustainability, and economics they all come together. And coming to skills, I'm sure they're still important now, but increasingly they will become important where the decision making is necessary under uncertainty and cross organizational or cross or international negotiations, and also having clear and credible communication skills. I think those will become very important for systems engineers going forward.
Yeah, I feel like a lot of what you mentioned is like Isaac Asimov's sci-fi book where his iRobot and Robot Visions kind of led to. So I think yeah, you're very much on track, and maybe yeah, it's not 100 years down the line, it's actually just 10 years. So yeah, we'll see. I'm excited for that future. And Hamed, I'd love to hear your thoughts as well.
I am glad you mentioned that point, because I'm afraid I'm not as optimistic in how the future is all sci-fi as we have seen in the last at least 15 years that I have been in the industry. Since even the beginning, machine learning was big 15 years ago. Everyone said it's the future. It's going to replace systems engineering. Model-based systems engineering will be done fully autonomously. 15 years now in, it's not really the case. So it might be a bit of a longer stretch of time where AI and machine learning and whatnot of model-based systems engineering starting taking over, and then the humans retain just the higher level things. I tend to believe systems engineering will still be strongly there as it had been 60 years ago, as it is nowadays. I like to think that we passed the bit of an attack on systems engineering, or the idea that systems engineering is an overhead that you can just skip it and then do the critical parts of subsystems and then they will work magically together. I tend to believe we are now at an era where the value of systems engineering is understood more. We still have factual data finally that can support the image of systems engineering to be fundamental. Otherwise, your failure rates will stay at a similar level like they were a couple of decades ago, while your cadence of launching satellites or the amount of satellites even in orbit is increasing, you still maintain similar failure rates. So in the background of things, I tend to believe systems engineering is here to stay, as they say. The foundation of systems engineering is basically physics, as a couple of my colleagues mentioned. So it's not going to disappear. It can be optimized, definitely. It can be polished around the edges. It can grow into more disciplines, and hopefully, and from what I'm seeing, the change of spacecraft level or launcher level to constellations and mission architecture level, and usually you see these roles happening now and taken over by systems engineers, rather than in the last 10 or 8 years have been taken mostly by the commercial side of things, as in sales management or project management or analysts and whatnot. So I can see now that the industry itself is evolving, and it's maturing to realize that systems engineering can evolve to take over these mission architecture planning phases instead of the commercial side of things, which gives the flavor of engineering and brings in all the engineering cohort and all the engineering efforts of building a space mission into realistically fulfilling that mission from also the commercial side and the physics side of things. So I'm really optimistic how systems engineering will be taking place in the future, and looking forward to seeing how it evolves.
Great. Thank you both for kind of showing us what you envision the future to look like. I think we can all agree it's definitely going to be something we can't even imagine right now. Things change so fast every day. I feel like things are evolving. But yeah, thank you both for those insights. So we're nearing the end of our kind of planned questions, and we have a bunch of audience questions we'll be pivoting to in a little bit. But I'd like to end my set of questions with a more fun one about what is your favorite book that highlights systems engineering? And I'll kind of kick things off to inspire all of you. But my favorite is a Digital Apollo book, which is about kind of the hardware software integration that happened in the Apollo era, especially with human in the loop, and how that kind of evolved from a lot of the astronauts being, fighter pilots and having that fly-by-the-wire control, and how that evolved into more automated and also not automated landings and activities. So that's my favorite one. I feel like everyone in the space industry should read that book. But we could start with Daniel to give his recommendation next.
Yeah, I was thinking about that, and I didn't want to list the textbook per se. So I'm gonna go with maybe an unorthodox answer and say it's Project Hail Mary, which is a sci-fi book. But why I thought it's actually it's one of my favorite books, and why I thought it's also a great system engineering book, it's because the main character has to deal with unexpected failures, limited resources, having to understand how different systems work, even though he's not an expert in it. It's constantly doing trade-offs. I think it's, as system engineers, we know that this is everyday life. Something new gets thrown at you, and the analogies are there in the book, although you will not learn how to become a system engineer from it.
Yeah, that's an amazing book, and I think the movie comes out at least in the US this weekend.
I think so, yeah.
Yeah, I'm very excited to see how Ryan Gosling takes the mantle.
Let's see.
But no spoilers here, but
No
I'm
spoilers.
very excited for that one as well. Great recommendation. Next, Hamed, would love to hear your thoughts.
Sure. I honestly would struggle to bring a name of a book right away. I think similar to what Jill mentioned, systems engineering is a role you grow into. I would say systems engineering mainly is something you harvest by experiences of working on multiple disciplines. The NASA handbook perhaps is the holy Bible of space engineers when it comes to systems engineering. It controls all the foundations of things, but if you would be in enough missions and enough moments when things go wrong, I tend to believe that's the best educator for systems engineering.
Great, thank you. Mamatha, would love to hear your thoughts.
I would say on the technical side, SMART is still good, space missions engineering. I still like it. I occasionally refer to it as well. But on the other hand, I also like Thinking in Systems, a primer. It's from a lady called Meadows. So although it doesn't look like a typical systems engineering book, and that's exactly the point of it, that she teaches how nonlinear behavior come into play, and recognizing how well-intended interventions would actually help, understanding feedback loops, delays, etc. So that in that way, I really enjoyed reading that book.
I will have to check those out. I haven't heard of either of those, besides, the smart one, of course. Next, Ryan, would love to hear from you.
I'm going to go with an Apollo era book, just like you as well. I have a copy of it. It's called Manned Spacecraft Engineering Design and Operation. I don't know if you can see it with the camera.
The blue lander is in the
Yeah.
way. Yeah.
This is the 1965 copy from NASA Manned Spaceflight Center Technical Library, which is now Johnson Space Center. So very special copy that was given to me. But this manned spacecraft book is free as a PDF online. It's been copied now, and it is systems engineering just at its absolute basics. In 1965, they were just taking the ConOps of what they needed to do, decomposing it to the functions, and then writing the requirements for the hardware to go get it done. And they tell a really excellent story about that. They've combined lectures that they've given at University of Houston and Rice in Houston, and really excellent book that is really the foundation of systems engineering.
Yeah, a really great recommendation, and seems like you have a historical copy, so very cool. Maybe we can get the collector's edition next. Mamatha, would love to hear. Oh, sorry, you already went. Matteo, you're next. Let's hear from you.
So I would say the European Cooperation for Space Standardization Handbook. No, I'm joking. That is really boring. I've read many pages too many times. I would have gone for Project Hail Mary, but since that has been already taken, Another from the same author would be probably The Martian, where also you see, I mean, the main characters re-engineering some of the components in order to survive 4 years or about 1 year of food and trying to decompose the problem in order to find the solution to sometimes simple, sometimes more complicated to survive.
Martian is, of course, a classic. I think, yeah, my license plate is actually G2G Mars from kind of inspiration from that. Um, yeah, whoever hasn't read it, definitely go out and read it as soon as possible, immediately. Next, Jill, would love to hear from you.
So yeah, I'm not endorsing a product for sale, but I would say
Yeah,
that
this is
probably
completely, we don't get any,
gotta put the
yeah,
legalese out there right up front.
yeah,
But
yeah.
personally, I think one of my favorite probably adaptations of systems engineering books would be The Fifth Discipline by Peter Senge, because it really connects the systems perspective to organizational leadership, and I find that a little bit more applicable in my current role.
Yeah, I hadn't heard of that one, so I'm taking notes.
I'll send
And
it to
then,
you.
yeah, definitely. Marcos, last but not least, let's hear what your favorite one is.
I think I'm just gonna go back to the basics here. At school, when I was still doing my master's, I really enjoyed reading the Applied Space Systems Engineering series, including also the SMAT, both from Larson. I think they were very good at teaching me the fundamentals that I needed to really understand what space systems engineering was, and so those will be my picks.
Well, I think we all have a combined library of reading to do next, so I think it's looking like a busy spring heading into summer. But now we will pivot into audience questions. So I'll just kind of list them out and kind of call on our panelists to answer specific items. So first is kind of one for me. Will a recording of this be available later? And yes, it will be on the YouTube channel, so you'll be able to rewatch or yeah, maybe catch a part you might have missed. So next, this question is for Marcos and Hamid. It is related to space debris. So with the rapid shift toward modular and commercial space systems, what are the biggest legal or regulatory hurdles the committee sees in ensuring long-term mission safety and debris mitigation? So
Yes.
we can start with Marcos. Yeah.
Yeah, from what we have been doing at our company, I think the global picture that we have is that, these new systems, these new space systems that we're developing faster than we can regulate them. But at the same time, these regulations are not as easy to build simply because, we often have regulations at national level, let's say, but space is global. Which also means that there needs to be some compromise or there needs to be some talks at a regional and even global level to how we will regulate this new space ecosystem that we are creating. I really like what we are doing here in Europe. I guess the example is what the work that is being done with the ESA Zero Debris Charter. Think of it like the Artemis Accords, but for space sustainability in Europe. Basically, every ESA member state, but not just the agencies, also the private industry can sign up for it, and they're involved in technical discussions. And we have technical groups. We have discussions on all several themes about sustainability, not just on the regulation side, but also on how to develop these new systems, new technologies that we might need to accomplish all of these new objectives based on the new guidelines for space debris management drafted by ESA recently. So I think this is a good example of the efforts that are being made to, regulate the new commercial space systems that are coming up. I don't know, Hamid, what are your thoughts?
Honestly, Marcus, you said it all. I can fully agree, and it's rare to say in the space field, at least, that I'm very proud of what Europe is doing on that frontier, because the biggest hurdle I see from the regulatory side or the legal side is actually it's more prone to accept pressure from the commercial market itself than the engineering aspect of systems engineering or of what we're doing in space engineering in general. So you could see some of the legal aspects or some of the regulatory aspects having a pushback from whoever is talking in the press or in the commercial market, and then they will dial back on the regulatory side of things, which would affect how they put restrictions and laws that can come in quickly and can come in and actually fix issues that we are seeing. So this is the biggest hurdle I can see from my point of view. We actually do need some regulations in the work we do, and to maintain space as an environment and protect this vulnerable field that we work with. The regulatory aspect is not the worst thing to have. We just need to have a regulatory aspect which is strong enough to move through with the criticism and with how loud the commercial market can be demanding it to be faster, to be more agile, to be whatnot. Because eventually what doesn't come loud or what doesn't come to our ears is the cost of failures. And when failures happen in space especially, it's very difficult to clean it up afterwards. So I tend to believe this is one of the biggest hurdles that we're seeing now.
Great, thank you both for very well answering that question. Next one is for Matteo and Jill. So the person asking the question is a mid-career hardware embedded engineer, and they're interested in pivoting to space systems engineering. So do you guys have any suggestions for that? I'm kind of thinking in mind a more next gen, new gen kind of person trying to pivot. So we could start with maybe Matteo for that one.
Well, yes, I think this goes really in the direction as well of what Jill mentioned, the depth versus the breadth of the career path. I suppose, I would start looking at what is available in terms of resources, even for free on the internet, to start reading, creating a foundation. And then looking more into, if this person wants to signal that the pivot as well to the employer, maybe certification like the INCOSE certification, that could be a good stepping stone to signal that this person wants to move more in system engineering role.
Yeah, I think I would add to that is to continue to be curious, ask the right question, ask smart questions that maybe aren't in your area, and find an advocate. Ask for mentorship, ask for somebody for help, and don't be quiet about it. People always, in my opinion, people want you to succeed, whoever you are. They want the best for the mission, for the agency, for the organization. They want what's best. So they see you asking good questions. They see you wanting to do this and being curious, and they'll try to help. So to Matteo's point, be curious, learn more, get additional education around you, and however that is, and then find an advocate.
Yeah, I think those are great suggestions. And just to add from my own experience, also you can kind of reach out to anyone on your team who's doing a role that you think is really cool and be like, hey, could I do a task for you, like a stretch assignment? And most of the time they're going to say yes. And then that way you can kind of prove your capabilities and your ability to learn. And then they can pull you in the future when there's a job opportunity, they can pull you in. I've done that a lot myself. I was on a software team doing systems engineering. I wanted to do more mission operations, mission ConOps planning. And so I reached out to that team and, started off small, doing some small things. And then they saw I could take on more. And of course, like work with your manager, obviously. But I don't think anyone would say no to that. But just go and ask. And the worst thing you can hear is no, is my personal advice as well. And then we can end the Q&A with one last question, and Hamed will answer this one. So how close are we to seeing quantum resistant encryption as a default requirement for all new satellite bus architectures?
Right. So everyone's scared of the point that comes in the future that their spacecraft is not ready to handle a new technology. We have seen this with on-orbit refueling and on-orbit maintenance, and everyone, had this experience of, oh, we did not design the spacecraft with ports, and some people started panicking on what is our spacecraft going to do. These technologies take time. they are not as close in the future as I would imagine. Not even 5 or 10 years. However, 5 or 10 years is the timeline that some of the demonstration missions and demonstrators that will go out working on these technologies. So these demonstrators are actually to start having some sort of a failure or success methodology proof, and then moving on from that. I tend to believe it's 5 to 10 years. However, keep in mind that most spacecrafts at the moment are still having crypto description, encryption planning into it. Everyone is designing with this HNDL system of harvest now, decrypt later. Everyone is scared of this to be a pain point in the future, so people try to lay the ground for it. But in all honesty, I tend to believe 5 to 10 years is a realistic form when it comes to be standardized.
Great, thank you for, I definitely don't know about that, so thank you for informing all of us, I think. But with that, I think we are at the end of our amazing panel webinar. So I want to thank all the panelists and my fellow committee members, and just also the IAF for helping us host all of this. And stay tuned for more amazing panels and webinars from the IAF Workforce Development YPP Committee. And yeah, I think that's everything. So bye everyone. Have a great rest of your day.